All right, today's video we're going to talk about shifting, and when we talk about shifting, what we need to focus on is the actual bit level, because that's what we're shifting. We're shifting by a certain number of bits, the actual binary values. Oftentimes what we'll see, especially when we use something like the dump regs function inside of our programs, we'll see those registers and the values represented in hexadecimal, and so it can be a little bit confusing when you first start off with that, and that we're actually shifting by the bits, we're not shifting by bytes, although you can shift by enough bits to shift by a byte. We'll have several shift types that we're going to talk about. We're going to start off with the logical shift, and the logical shift is pretty straightforward, and that when we shift all the bits either to the left or to the right. The incoming bits, so when we shift by any number of bits, we shift one bit to the left, we add another bit. If we shift one bit to the right, we add another bit. And those bits that we add are always going to be 0. So no matter what direction we shift, we add zeros on. You can shift by any number of bits. You can shift by 1, by 2, by 3, by 4. It doesn't really matter. So you can shift by any number of bits. You can also use CL in order to shift by. So I won't use CL in any of the examples. You may or may not see it, I guess, outside of the class. But typically we'll do a shift, and I'll just use an immediate value or a constant value. Also, when it comes to shifting, when we shift, the last bit shifted out sets the carry flag if it's a 1, right? So if the last bit that we shift off is set, if it's 1, then we also set the carry flag. So we'll look at an example here. Here's our original value, and we can see that this is 8 bits, 1 byte. We could look at this in hex if we wanted to, and this would be an E, and this would be an A, because here's our divider there. There's 4 bits and 4 bits. So if we shift it to the left, then what we're going to do is we're going to shift the leftmost bit off, and we're going to add another 0 bit on, right? So we shift this off, everything moves over 1 bit, and we added that 0. Because we shifted this bit off, and this happened to be a 1, this would have carry flag set, right? So we would see that output in the flags register. Okay. Now, on the other hand, let's say that we take that same original value and we shift to the right. So now we're shifting this bit off, the 0, so that means we would not have the carry flag set, and we're going to add a 1 on this side, or a 0 on this side, right? And then from there we're just shifting every bit over by 1 value, right? And so that's how that basic shift works. Okay, so let's look at a relatively simple example. All right, so let's say that we move into AX the value FF hex. And then after we do that, let's say that we shift left AX 1 bit. Right, so it helps to look at that in binary. So how would we write that in binary? Well, we'd have all 1s. Okay, and now what happens when we shift? Well, if we shift to the left, we're going to shift that leftmost bit off. Change the color here. Hopefully this makes it a little bit easier to see. We're going to shift this leftmost bit off, and we're going to add a 0. So now we have, as a result of that, we have these 4 values, these 4 bits, and these 4. So now the result of that would be F, 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 and this would be E. All right, so let's go ahead and just start working with that in a program here. Okay, of course, took too long. There we go. Alright, then I'll go ahead and open this up. Every once in a while when my network freaks out, I've got to make sure that my client is still connected, so we'll try to get that going here. Here is the program though. So I'm going to move into AX all Fs and then dump the register. So you can see that here that the AX is set to all Fs. Okay. Next thing I can do is then I can say let's shift left AX by 1 bit. All right, and then we'll dump the registers again. And we'll see that. Right? And there's our result. So FFFE, and that is what we calculated. Right, and so we can continue to do that. What happens if we shift right AX 1 bit and dump registers? Well, now we have 7 FFF. And that makes sense, because if we think about shifting, let's just take that first 4 bits. If we shifted that to the right one, right, this is F, that equals F, then we'd have a 0, 1, 1, 1, which would equal 7, which is the response or the result that we got. Right, so again, logical shift, we're adding a 0 depending on whatever side, whether it's a shift left or a shift right. Okay, here's an example from the book, and we'll kind of walk through this similarly, and then we'll convert this into binary, and then we'll go through a couple of these commands at least together. We're going to move that value, so C123 hex into AX. We're going to do CLC, and what CLC is going to do is it's going to clear the carry flag. So we want to make sure that, since we might be looking for the carry flag to determine if a bit was shifted off or not, a bit that was set was shifted off or not, we go ahead and we clear the carry flag before any of these operations that leverage the carry flag. So we'll be looking at not only was the carry flag set, but what is the value in AX after each one of these operations. So to start off with, we have C, so 1100, then we have 1, then we have 2, and then we have finally 3. Okay, and it's very easy when you're writing these binary numbers down. So if you find yourself doing this for practice, it's very easy to make a mistake here. At least I find myself doing it all the time. So always make sure to kind of check yourself. All right, so shift left AX. Let's just change this color. So if we shift left, that means that we're going to shift that bit off, and we're going to add a 0 on. Okay, so we shifted off a 1, which means that our carry flag is going to be set. So I'll just put a 1 there to indicate that that will be set. And now we have, as a result, we have those 4 bits, those 4, and now these 4. So 1000 is 8, 0010 is 2, 0100 is 4, and 0110 is 5. All right, and now we can check to see, to make sure that that is in fact correct. So we can go back to our program here, and I'm going to comment out these dump regs just to help make sure we don't get too much clutter here. And I'll move into AX 0C123 hex, and then we'll shift left AX1 and dump the regs. All right, so let's see what we get for a result. 8246, 8245. Of course, I did my math wrong. Okay, so I can get this slide back up. Slide, and I'll make my pointer pen. Right, so this is 4 and 2, and then a 0. So that should in fact have been a 6. So it was a miscalculation on my portion. Okay, now we'd have a shift right. So we can go through that same process. And 8. So 1000, 2, 0010, 4, 0100, and then 6, 0110. We shift to the right, so we're going to shift this bit off. Carry flag is not set. Shift to 0 on, and now similar to the last process that we went through, we have these 4, these 4, these 4, and these 4. Right, so 1, 2, that would be 4, that would be 1, that would be 2, and that looks like 3. Okay, so 4, 1, 2, 3. Carry flag is not set though. Right, we can look at that last output and see that our carry flag was set. That was one thing I forgot to point out. Okay, so now we'll go shift right, AX1, and then 4, 1, 2, 3. 4, 1, 2, 3, which is what we got. Okay, and I'll leave this last one up to you if you want to complete it, just to make sure that you understand what's going on here. You could follow a similar process and just determine what is the value in AX, and then what is the carry flag set or not. All right, so why use shift? Well, it allows us to quickly multiply or divide by 2, and it's actually faster than doing a multiply or divide. And so oftentimes what you'll see, especially if you take the reverse engineering course, is that what compilers will do is when they see a multiply or divide by 2, they'll actually use a shift operation instead of multiply. And so they'll optimize your code for you. A good example of that, and we can go through just so you can see what I'm talking about there, is we can set up a loop, and we can loop through a value. So let's move into EDX32, and then we'll call this loop start. Okay, and what we'll do is we'll say, let's say that while I'll compare EDX to 0. Right, jump if 0 and loop, right, and then we got to create our end loop. Otherwise, we can shift right EDX by 1. Okay, and then we'll move into EAX EDX, and then I'll call print int, and I'll call print new line, and then we'll do a conditional jump back to loop start. So in the previous lecture, we ended kind of talking about that while loop, and so this is more of your while loop structure, and that we start the loop. So I do a little bit of initialization here. We start the loop, and we set up whatever instructions we need in order to perform our comparison. So I'm saying that as long as EDX is not 0, then go ahead and execute the instructions. As soon as the 0 flag is set, so as soon as EDX is 0, then we're going to jump to the end of the loop, which takes us to the end of our program. We don't make the jump, we continue to execute these instructions. And then from here, we'll shift EDX to the right. And then from there, this is simply just a few instructions to move EDX into EAX, call print int, and call print new line. So let's save that, and we'll see what happens. What you'll see is that it's like dividing 32 by 2 in this loop. So you can see there we started with 32, we divided by 2, then we printed, so we had 16, 8, 4, 2, 1, and then 0. Right, so it's just a fast way to do that. And you can do the same thing. In this case, it's like dividing. You could do the same thing with multiplying if you wanted to. Right, so there's just one example. Arithmetic shifts, right? So one of the problems that we have with that last example was what about when we have to worry about signage, right? If we're shifting left and right and we're simply just adding a 0 on, if we shift to the right, we will potentially lose that sign bit. If we shift to the right and the most significant bit was a 1, and we shift that over 1 bit and shift a 0 in its place, then we've lost the signage. So we've changed the signage, the value of that number. So if we're doing something like using a shift to divide or multiply, then that obviously would change the outcome of our results. So we have a couple of different instructions. We have the arithmetic shifts, and what the arithmetic shifts do is they ensure the sign bit is treated correctly. So we can shift right, this keeps the sign, and what that is essentially doing is it's just replicating the most significant bit. It will not be shifted, new bits are copy of the sign bit. So that way negative number stays the same. So we have SAR as the mnemonic. Shift arithmetic left is actually just a shortcut for shift logical left, or SHL. And so while shift arithmetic right, because if we're shifting from the right, we can copy that sign bit. When you shift to the left, because we're shifting from the left, or shifting a new bit on from the left, or on from the right, we could potentially lose that sign bit. And so even though there is a command for arithmetic left, it does potentially shift off the sign bit, and so you may lose the signage of the number. So the only way you can ensure that you're keeping the sign is to do a shift arithmetic right. All right, so let's take a look at an example of that. Okay, and again, I'm going to go ahead and comment out some of these prints just so we don't get so much clutter in our output. Okay, so let's say that we move into EAX a value of -7. And now I'll dump the register so we can see what that looks like. Okay, so there it is, EAX, all F's and a 9. So we know 2's complement. We would invert those bits and add 1, and that would give us our -7. Okay, so let's say now what we do is we shift to the right EAX by 1, and then we dump the registers. So what does that give us? And we kind of saw this in a previous example. Right? This is no longer a negative number because we have 7, and 7 in binary would be 1110. Right? So we've lost that sign bit because we simply shifted a 0 in its place. Right? So instead, what we could do, and we could do is shift arithmetic right EAX by 1. Okay, and you can see now that between this dump regs, which is our original value of -7, now we have FFFFFC. Right? So we kept the sign bit, we shifted all the other bits. So in this case, we shifted 31 of the 32 bits because that most significant bit stayed the same, and we can see that our value did in fact change. Okay, and let's see, let's go ahead and take a look at the next example then. Right, so this is very similar to the previous ones that we've been going through. Right, so if we have, we move into AX, C123 hex, and then we shift arithmetic left AX by 1, what is an AX and what is CF? And so we can go through this as an example, and we can convert that to binary. So we'd have 1100, 0001, 0010, and then 0011. Right, shift arithmetic left. So in this case, it's just the same as a logical shift. So we're going to add a 0. We're going to drop the leftmost bit, and it happens to be a 1 that we're moving in this place. So our new value then would be this. Those 4, and those 4. Okay, so 1, that's 8. 0010, that's 2. That's 4, and that's 6. 8246. And we saw that actually in a previous example. Right, because we moved into here and then we shifted left. So if we look at the dump regs for 3, 8246, you can see it's going to be the same value. So I'll come down here . I got these off a little bit. Let me get those updated. Okay, so I'll move into AX 0C123 hex, and then we'll shift arithmetic left AX by 1, and then dump regs 7. And I'm going to comment those out too. 8246. Right, so there's the same result. Okay, so here's our value, 8246. What did we shift off? A 1, so our carry flag is set. Now we shift arithmetic left again. That's really the same thing as shift logical left, and we've already done that, so we can just go back just to save a little bit of time. Actually, we haven't. So we could do that as well. So we have 1000, 0010, 0100, 0110. Okay, if we shift arithmetic left, so we're going to shift a 1 on, we're going to shift this off. So again, our carry flag will be set, and now we have these 4, and now these 4 bits, and these 4 bits, and these 4 bits. So 0, 4, 8, and 12 would be C. So 048C. Okay. Shift arithmetic left, AX1. 048C. right? And we can see that result right there. Okay, and then the last thing that we would do, or that we're doing here in this particular example, is shift arithmetic right. And so again, we could take all these values and we would just move everything to the right. We would copy the sign bit though, and since it's set to 0, in this case we'd copy a 0 on. And so instead of working through that example, we'll just go ahead and we'll just do it here in our code, and then we'll run that and see what we get for an example, or an output. So 0246. Okay, that would be the result there. So you could figure that out, you could calculate that, just like we've been doing, right out the back binary, look at the sign bit, so it's a 0, so you'd add a 0, you'd shift the 0 off, so we would have a 0 flag not being set. All right, and again, we can check that. So the carry flag's not set, so we'd have a 0 there, and that'd be our result. So we can continue to figure that out. Okay, the next type of shift then is the rotate shift. And what happens with the rotate is that the bits that fall off, they go to the other side. We just rotate them on. So we have rotate left, rotate right. This one, I think a good example for this is to look at, let's say that we move into, let's use a full 32-bit register. So let's say I move into EAX 0000FFFX, right? And we don't actually need all those leading zeros. Okay. What does that register look like? Regs. Right, so the upper 16 bits are zeros, lower 16 bits are Fs. Okay, and now what if we do a rotate? So let's rotate to the left EAX by 16 bits. Okay, what happens? Well, you can see that we just move those 16 bits to the left. Okay. Well, what happens if we want to rotate EAX by 24 bits? And then we dump the regs. All right, we just rotated around. Right? They didn't fall off, they didn't disappear. They just rotated back around. So once they started falling off, in a way of speaking, then they came back around. Okay, so that rotated. So we'd already rotated 16, and now we rotated another 24. So that's why they kind of popped up in the middle. Let's say that we only want to rotate by an additional 8. Okay, so what does that look like? Well, if we have the upper 16 bits, and now we're moving that another 8 bits, then we've essentially rotated those top 8 bits off. They've come back around, and then these two moved up. They've shifted to 8 bits to the left. Okay, and that's what we see here in this last register dump. We see that we've rotated them, essentially split them in half. We have those two still at the topmost, and now those the uppermost were rotated around. Okay, and rotate left works as similar as rotate right. So I could say rotate right EAX by 8, and what that would do is essentially put them right back to where they were before the previous instruction. Right, so there we go. So we rotate around. Okay, there's another instruction, and that's rotate with carry. And so what happens with the rotate with carry is that we actually, instead of setting the carry flag based off of whether we rotate a 1 off or not, set bit off or not, we actually use the carry flag as part of the rotation. And so let's say that we take an 8-bit value, 1010, 1010, which would be A and A. We also use the carry flag. So now if we rotated that using RCL by 1 bit, we'd rotate, Right, another rotate instruction is rotate with carry. And what happens then with rotate with carry is that you actually use carry flag as part of the rotation, as part of the bits that you're using, which means that you may have to set the carry flag as well if you want to use, because you're going to use that as part of your bits. So as an example, let's say that we have the value, let's say AA, which you can see that I've already written out here. So 1 0 1 0 and then 1 0 1 0. Carry flag is part of this, and so we need to make sure that that it's either cleared, right? So we have CLC to clear it, or STC, which is the set carry, right? So it's either going to be a 0 or a 1. And now we can rotate with a carry left or rotate with a carry right, which is our two examples here, that just rotate. And just like the previous rotate, the only thing that we add in now in addition is the fact that we use this carry flag, right? So if we rotate it to the right, we would rotate the 0 around, so that would become a 0 here, and everything would shift into that carry position, right? And so we would just rotate using the carry flag in kind of a wheel or a circular fashion, whether you're doing it to the right or to the left. Right, and here's an example. I think we've gone through quite a few of them now, so I'll just leave this again as an exercise for you to work on. I've also, reason why you have numerous or several attempts for the quizzes to help with that as well, just to make sure that you get a chance to practice and get some feedback to know that you're doing it correctly. So, all right, bitwise, I want to talk about the test. So those were the shift and shift operations. The last thing we're going to talk about is test. We've been talking about bitwise operations, and we had bitwise OR and XOR and NOT. The last one is test, and what test does is it performs a logical AND on the operands, but it only sets the flags. It does not destroy registered data. So here's some more examples. If we look at this particular example, just to kind of go through as a refresher some of those bitwise operations, if we have our same value we've been using, so 1 1 0 0 0 0 0 1 0 0 1 0 and then 0 1 1, I'm sorry, 0 0 1 1, and then we do an XOR with that with this value here. So we're XORing this value with this value. Right, what does XOR look for? Well, XOR looks for exclusion. So if it's 0 0, it's 0. If it's 1 0, it's 1. If it's 0 1, it's 1. And if it's 1 1, it's 0. So it's only going to be a 1 when the two bits are different. So if we have for E 1 1 1 0, 8 1 0 0 0, 3 0 0 1 1, and then 1 0 0 0 1. Right, and now we can go through and we can look for the results of that operation. So 0 0 1 0, 1 0 0 1, 0 0 0 1, and 0 0 1 0. Right, and so that would be the result. So 2 9 1 2, and we can take a look at that. Okay, so I'll get logged in again. Apologize that I have to keep doing this. I'm not sure why my session is timing out so rapidly. Okay, so I'm going to get rid of a couple of these dump regs again, just because I'm generating quite a bit of output here. So let's move into AX0C 1 2 3 hex and move into well, we don't need to do that. We can do XOR AX with 0E, and let me just double check those values. 831 hex. Okay, and now we'll dump regs because we're interested in seeing the output that is in AX. Okay, 2912, and I got 2912. Right, so you can see that that's actually what's happening when we do an XOR. Not relatively straightforward, just negating. So we take all these bits and we just invert them, and so the result of that would be the inversion of the bits for that number. All right, to get to this actual example then of the test instruction, let's take a look and see what would happen there. All right, we're looking at what flags are being set. And so if we move into AX 0C 123 hex, and then we do a test on AX 0C 123 hex, what do we get? Okay, we see that no flags are set. And so we're doing a logical and what the logical and is doing is it's very much looking for the same conditions as when we do a compare. In order to get a 0 flag to be set, we'd have to have something like this. We'd have to have where we have, let's say, 0 FF hex, and then we test with AX. 0FF00 hex. Sorry, I had to think about that for just a second. All right, so now when we run this test, let's see what we get for an output. Dump regs, we should see that register dump regs 13, the 0 flag is set, right? Because if we take these two, right, we do a logical and what does a logical and look for? Logical and is looking for them to be the same. So 1 and 1 would be a 1, 1 and 0 would be a 0, 0 and 1 would be 0, and 0 and 0 would be a 1. And so in that previous example, if I'm testing FF00 and 00FF, right, we're going to get none of the bits are going to be the same. Right, because we'd have 1111, 1111, 0000, and then we'd have the exact opposite of that. Right, so now we do a logical and on that. Oops, I'm sorry. Right, none of them are the same. So all of these would be 0, which means the 0 flag would be set. So when we looked at this result, the 0 flag would not be set because all of those would result, if we compared, so just for example, let's take C and we compared that, we did a logical and we get the same thing, right? So we wouldn't get a 0 flag being set. Right, so that's kind of how we can use test, and oftentimes you'll see tests being done in some instructions just to test for those conditions without destroying any of the registers. All right, so here's some examples, again, right out of the book, so you can see what are the values. So just again, it's just another resource to help understand, make sure you understand what's going on, moving that same value that we've been working with in this entire video here into AX and doing an OR, an AND, an XOR, another OR. The nibble is, in fact, half of a byte, so it's 4 bits, so it's kind of a joke, it's kind of, but it is 4 bits. And so that's it. That's all I've got for today. So, let me know if you have any questions. Otherwise, we'll pick up next week and go from there. All right, thanks.